Good evening, everyone. Thanks a lot for joining me today for this talk. I'm Ankita. I belong to storage and caching team at Pinterest, and I will be talking about how Pinterest used TiDB to modernize their HBase workloads. So this is the agenda for today. First, we will go through some introduction, motivation for adoption of TiDB, how we built our in-house TiDB platform, how we did data migration for one of our bigger use cases, which is 4 terabyte without any downtime. After this exercise, what were our big wins, and then future work and Q&A. So what is Pinterest? We already got an introduction, but let's do it again. Pinterest is a visual discovery engine for finding ideas like recipes, home and style inspiration, and much more. The mission of our company is to bring everyone the inspiration to create a life they love. Our engineering is a little more than 1,000 people. I belong to data engineering, which is the org. Its mission is to build and run reliable planet-scale efficient data and AI platforms and services for Pinterest. The data engineering has around 8 to 9 sub-orgs, and online systems is what I belong to. The mission is providing reliable, simplified, and efficient online systems to enable fast product development. So we are a platform team. And my team is storage and caching. I'm part of online systems. And our mission is to provide reliable and high performance online storage and caching services for better winner experience. So this is a high level technical stack. Our team manages HBase, all of the HBase ecosystem at Pinterest. There are a lot of services built on top of it. First is Zen, which is a graph database built on top of HBase. Exia, which is a secondary indexing store built on top of HBase. Sparrow, which is a transactional database built on top of HBase, and UMS, which is a KV store. And all of these services are actually serving these business critical use cases like smart feed, follower service, trust and safety, ads indexing, shopping use cases, virtual try-on, etc. We have more than 300 use cases being served from my team. All of which are currently served by HBase. So this is the HBase footprint. We have more than 50 production servers and more than 9,000 virtual machines, one of the largest production deployment in the industry. We serve 6 petabytes of data on disk and 100 plus business critical use cases. So what is the motivation for next generation storage backend? So as you saw, we have built so many services here to on top of HBase. This is because there are a lot of natively lacking functionalities. For example, transactions are natively lacking. That's why we worked around it by building a service on top of it. Similarly, secondary indexing is lacking in HBase. That's why we had to build Exia to support such use cases. And similarly for graph service. So with by building all these services, our architecture and ecosystem has become so complicated that that we all came together to try to simplify it. As a result of this complication, it also has a very high cost. So as I explained, Exia is a secondary indexing service built on top of HBase, and due to lack of native support of secondary indexes, it contains 5 additional components. For example, Kafka, HBase CDC system, which is again a homegrown system, and indexing engine called Muse, which is again a homegrown service. So even after this, Exia supports only eventual consistency, and the window is between 5 milliseconds to 2 minutes. We still can't support strong consistency. Similarly, in Zen, due to lack of cross-table transactions, there are data and index inconsistencies created, which are resolved by offline jobs. So these offline jobs, although they run every night, they have been a major pain point for our customers due to inconsistencies created. Secondly, inefficient data retrieval due to lack of composite index in HBase. So why is it so costly? First is our on-call is extremely heavy. We get around 40 to 50 pages in a week, and we have a very high KTLO. The HBase version which we are using is 6-year-old and is end of life. The tech debt which we have accumulated over so many years makes it very hard to even do a version upgrade or maintain it. We have a primary and secondary setup for each of our production cluster. That means we have 6 replicas per unique data set. This is because even in HBase we have HDFS, which is the block storage, and HBase is the serving layer, which uses region servers to actually serve the data. It is a single shard architecture, but underneath it there are 3 blocks for each data set. So that's why even though we have primary and secondary cluster pair, each has a total, we are maintaining 6 replicas, which is very costly. So this is our vision. We wanted to unify and simplify our architecture to first have like a new data access layer, which is multi-API, multi-data model, and multi-backend, because a lot of components of these services are common. For example, authorization, authentication, rate limiting, etc. So we wanted to implement them only once. So that's why we decided to build a new service structured data store. And we also wanted to investigate if there is a better new SQL database which can replace HBase, which has the scalability of NoSQL with the rich SQL-like functionality of MySQL. So this is our journey. In H1 of 2020, a working group was formed with like 5 or 6 engineers of storage and caching team. In H2 of 2020, we evaluated more than 15 storage backends and did performance benchmarking, in-depth performance benchmarking and shadow traffic for 3 of them. They were Yugabyte DB, Cockroach DB, and TiDB. In H1 of 2021, we had finalized that TiDB is our next-gen storage backend. So we continued with the shadow traffic, TiDB reliability testing. We onboarded our TiDB platform on Envoy. Envoy is a proxy which is used across Pinterest for various services. And we started work on backup and restore. In H1 of 2021, we worked on data migration strategy for HBase to TiDB. Our first use case was onboarded to TiDB. We integrated TiDB with Monarch. Monarch is the Hadoop platform at Pinterest. We integrated the TiDB monitoring stack, which is based off Prometheus and Grafana, with Stats Board, which is a Pinterest-specific monitoring system. And we started SDS design, which is the unified data access layer here, which is shown here. Then in H1 of 2022, we had productionized TiDB and had built our own platform, but there were a lot of reliability issues. So we spent all of our time ensuring that the platform we are building is rock solid. So we worked on reliability improvements. There were 3 more use cases onboarded to TiDB platform. Backup and restore was productionized. SDS PRR, that means the SDS system was, again, it was ready for production. PRR means production readiness review. And we started working on TiDB offline framework. So TiDB offline framework is basically analogous to what we have in HBase. By offline framework, I mean that every night you basically snapshot all the tables and put them in S3 so that it's ready for clients to do their analytical queries. So the advantage of this is S3 storage is cheaper, and at the same time, you no longer will affect the online traffic no matter what the query is. So we do this for most of our tables, which are served by Zen, Ixia, etc. And we want to have the same feature parity in TiDB. So we started working on that. So now let's change gears and see how we do manage TiDB at Pinterest. We don't use TiUp, which is the one-stop deployment tool. This is because there were many overlapping features like deployment service, certificate management, monitoring stack, and operational tooling, which was overlapping with what Pinterest has. For example, Pinterest has a company-wide certificate management service, which is deployed all over the fleet. So similarly, all of these are different sidecars or microservices. So the amount of effort it would have taken to work around this was too much. That's why we decided to build our own TiDB platform by building from source code. So we maintain the TiDB source code in Fabricator, which is our internal Git, as a monorepo. There are more than 5 components in TiDB ecosystem maintained as Git subtrees. We have done more than 3 version upgrades, and the last upgrade from 5.4 to 6.1 only took 1 engineering day. This is a snapshot of how the TiDB build and release pipeline looks like. As you can see, we have a lot of components of TiDB. For example, PD, TiDB, TiFlow, TiKV, dashboard monitoring, etc. So all of them are actually built in parallel via a Jenkins pipeline. All of them are, so this basically creates one Docker image, which has all the binaries packed into it. And you can run this you can run the Docker container from this image as needed. So now let's see how we are managing the TiDB clusters. Each TiDB component is a unique environment in Telatran. Telatran is our deployment service, which is used for deploying all the services at Pinterest. We have the ability to horizontally scale SQL and TiKV by a click of a button. All TiDB clusters are TLS enabled. We use their native TLS to ensure that they're enabled. And these clusters are accessible from an Envoy port, which is a proxy used at Pinterest. This ensures that they are AAA compliant. This means auditing, authentication, and authorization is all provided by Envoy. This is an example of TiDB cluster, how they look in Telatran. So for example, shared vanilla prod PD will connect to shared vanilla prod of TiKV. So these are our production clusters, shared prod, shared vanilla prod, and all these. So one TiDB component is a Telatran environment, and this is a stage. So each stage is unique and connects to the same name for the different component. So since we built our own TiDB platform at Pinterest, it has been a bumpy ride and with lots and lots of learnings. These are a few important learnings I would like to share. First is the split brain problem. So as we said, as I told you here, when you spin up a new PD in, say, shared vanilla prod, it will come up and then create its own etcd quorum. And at the same time, the TiKV machines, which are in this shared vanilla prod, will try to connect to that PD. Now, if in the etcd quorum, so for example, you have 3 PDs and the cluster is healthy, and suddenly a PD dies, okay? Now, when a new PD comes up, it's possible that the earlier HCD quorum, it's not being deleted. So it already has 3 members. So it won't allow this new PD to join the quorum. So it will form its own quorum, and then the some of the TiDB nodes connected to it. This was a problem which was hard to diagnose because there was no error anywhere. The fix was simple, basically to ensure that if the new PD which comes up is already it won't come up until the HCD quorum is less than 3 members, because we don't want 2 quorums, right? We only want 1. Then host isolation logic for replica placement. TiDB already provides this feature where you can choose if you have a 3 replica cluster, you can choose to put it in different AZs. We additionally we are additionally using the feature of keeping 1 replica on each host. This is to ensure that no 2 replicas of same data set will exist on 1 host. That's because it's according to CAP theorem, if 2 replicas go down, then availability will be affected, right? And this can happen if 1 host goes down, which contains 2 replicas. That's why we ensure that 1 replica exists on 1 host of a particular data set. Leadership transfer logic was added to PD and TiDB startup scripts to prevent latency spike during deployments. So when we restart PD, normally what happens is it will, if a PD, which is a leader, is getting restarted, it will automatically transfer its leadership to another PD in the quorum. And similarly, for TiDB, it will transfer the leadership to another replica. But we realize that if we don't explicitly transfer it during startup, then there is a small window when there is a latency spike. So we added this you can say this logic in our scripts to ensure that before PD is restarted, make sure that it's not a leader. Similarly, for TiDB, if it's restarting, then whatever replicas it's serving, it should not be a leader for any of them.
Excuse me, if I may, I just want to ask a question about when did this transfer will be happen? So what's the necessity of the transformation about this PD from one to another? The case scenario of that. Am I clear?
Yeah, sure. So your question is when will this transfer happen, right?
Yes.
So so if you see here, there are these are 3 machines.
Mm-hmm.
These are 3 PD machines. And say if 1 host just dies, it's built on top of AWS, and a VM can just die, right? Without, it can just die. So if that dying VM is the leader, then internally TiDB can transfer the leadership to other hosts. But during there is a window during which this transfer is happening, where the client can see latency spike. That's why we ensured that at least when we are doing a graceful restart, we explicitly transfer the leadership and then do the restart. If it happens automatically, then nobody can do anything. We just depend on the system to gracefully recover.
I see. So it just provides an explicit strategy to preventing the incoming PD as a leader, because they need some one-up time to be. Okay, gotcha. Thank you.
Then we have now added TiDB alerts per PingCAP's documentation and integrated it with our PagerDuty, so that if something is wrong with our TiDB production clusters, the on-caller gets alerted. We have improved our wikis and internal runbooks to ensure that new members joining storage and caching team at Pinterest can ramp up on our homegrown TiDB platform faster. We have the ability to create an empty TiDB cluster in 4 hours or less with Telatran. We can perform instance upgrade and version upgrade with no downtime. And TiKV region transfer, we are able to do TiKV region transfer at throughput of 400 gigabytes per hour. So this TiDB region transfer, this is needed when you are basically, if you want to kill a TiDB machine. TiDB is stateful, right? So we want to make sure that those regions are transferred to other hosts before a host dies. So this is again similar to what we do in PD, where if it just dies out of nowhere, we depend on the system to self-recover. But if we explicitly are doing an instance upgrade or doing like version upgrade, then we want to make sure that the regions are explicitly transferred. This is because we use local disk. We are not using EBS as of now. So anytime host is replaced, that data which it serves has to be served from other hosts during the meantime. We have ongoing efforts to ensure to look into EBS in future. So now let's change gears and see how we did data migration for one of our use cases. So this is, we use Lightning tool, which is again provided by PingCAP. It has two modes, local backend and TiDB backend. The local backend mode is very fast. As you can see, it ingests data at 500 gigabytes per hour. And the TiDB backend, which is an online mode, it is a little bit slow and it ingests data at 50 gigabytes per hour. So one major distinction is during TiDB backend, the table can still serve online traffic, but if you are using local backend to ingest data, then that table is offline. It cannot serve traffic. So when we built our data migration framework, these were our goals. First is the data migration framework should be generic and it can be used for online data migration of all HBase use cases like HCL, Zen, Sparrow, etc. We should have a validation strategy to ensure that there is no data loss and we have acceptable percentage of temporary inconsistency by end of the exercise, which can be fixed with offline jobs within reasonable time. So when the data migration exercise is over, we want to ensure that there is an acceptable data consistency between HBase and TiDB. No downtime and should be transparent to the clients, should be repeatable and can be tested, and it should be able to support strong consistency use case. So let's go through how the strategy looks like. Initially, if this is the state, we have a client which is talking to a service. This service can be Exia or Zen or Sparrow, and it's being served from a HBase table. So during migration phase, you basically snapshot the HBase table and put into a CSV dump. Lightning uses CSV dump to ingest to a TiDB table. So basically, you are snapshotting HBase and ingesting the CSV dump generated from that snapshot to ingest data via Lightning to TiDB. Then once this TiDB table is ready, although by then there is some delta created between HBase and TiDB because the traffic never stopped, right? The clients kept writing and kept writing to HBase. So there is some delta between TiDB and HBase, but TiDB is still ready to serve the traffic. So what we do is bring start double writes from service so that it's synchronously writing to HBase and asynchronously writing to TiDB. What this means is if HBase goes down, then the client will see error because it's in the critical path. But if TiDB goes down, client will not see error. We are writing in via asynchronous path. After step 2, now we want to reconcile whatever delta which was created between HBase and TiDB, right? So how we do it is we snapshot HBase and snapshot TiDB. Then we store it in S3. We store both of these snapshots in a common format in S3. Then there is another offline job which reads these snapshots and compares rows which match and compares rows which match with each other. If they don't match, then it writes it as a separate output in S3 again. And then there is a third job which reads this second output, gets the latest value of a row from HBase via the service and writes it to TiDB. So one thing I forgot to mention here is, here we have assumed that we are okay with having a strict schema, because TiDB uses schema and HBase is schema-less, right? So before start of this migration, there needs to be, like, we did some exercise to ensure that the column names and column sizes and indexes, all of them were in accordance to our client's needs. And going forward, like if they want to add a new query, they have to tell us beforehand, which is an additional step which was not required in case of HBase because it's schema-less. So after this reconciliation step is done, we start double sync writes from the service to HBase and TiDB. This means that TiDB is also in critical path now. If any of HBase or TiDB go down, client is going to see an error. We did not implement rollback in this double write framework, which basically means if the write was successful in HBase and failed in TiDB, then we returned an error but did not roll back whatever was written in HBase. This was because we were able to run the reconciliation scripts as many times as needed in case if the system went down, and we were able to resolve the inconsistencies in that way. So after step 5, then now we are ready to deprecate the HBase table, right? So first we start writing asyncly in HBase, and TiDB is already in sync path. This is because we just want to make sure that if something bad happens, we have the ability to roll back to HBase in the best effort scenario. This step can only be used for use cases which can tolerate some inconsistency, because we are no longer reconciling HBase with the source of truth. Now we consider TiDB as the source of truth in step 6. And the final state is now client is basically served from TiDB. Yeah, so these were the trade-offs we did. First is inconsistency scenario due to storage backend unavailability. As I explained here, if any of the storage backend is unavailable during sync writes and it's successful in one and fails in other, we are not going to roll back in the one where it's successful. We are going to work around this inconsistency by running the scripts which we ran in this validation and reconciliation phase. Inconsistency scenario due to race condition between double writes and reconciliation. So if you see in step 4, we are basically reading the latest value of a row from HBase and writing it to TiDB. Now, during this small window, it's possible that a live write came and wrote to TiDB, and we are basically overwriting it with stale write, which we read from HBase. So this, even for this scenario, we decided to depend on our reconciliation scripts. This is because in practice, we saw that even with 400 QPS, 400 write QPS, this didn't happen much. Like we only had to run reconciliation scripts once to achieve 5 nines of consistency, data consistency between HBase and TiDB. These are some of our learnings in data migration. First is TLS certificate management. So yeah, so TLS certificate management, this was a learning which, like, it took a lot of time to realize that Lightning, it didn't have the feature of automatic TLS certificate refresh. So as I told you before, at Pinterest, we have our own homegrown service, which ensures that all the certificates are refreshed every 12 hours. Every 12 hours, yeah. So if during that window of certificate refresh, if there is a data ingestion going on, Lightning would fail and it won't say anything about certificate. It would say PD region not found. So we had to go through some series of failed ingestions, and then PingCAP team helped us by bringing in the SMEs to basically do the root cause analysis. And they have also shipped the feature of certificate refresh in 5.4. Second learning was between offline mode and versus online mode. So since offline mode is very fast, it has a throughput of 500 gigabytes per hour, and online is very slow. We decided to use offline mode for a cluster which was already serving traffic for a different table. But this offline mode, it's so resource intensive that it started affecting the latency of the production use case being served by the cluster. So we decided to separate the clusters for short term, and for medium to long term, PingCAP has provided some placement rules to ensure that if you are doing ingestion in a second table using offline mode, it won't affect the latency of another table in the same cluster. Exia double writes reliability improvements. So here this service was Exia all throughout this exercise, and writing a double write framework which is able to like go through async and sync mode for HBase and TiDB, it's pretty challenging, and it took us some iterations to ensure that it was reliable. Support for Java key store merged upstream for TiKV Java client and MR connector. So here, for snapshotting TiDB, we used MR connector, which is an open source tool in Ti Big Data, which is created by some other company, but they have open sourced it. So that tool didn't have Java key store support. And since I mentioned everything in Pinterest infra is TLS enabled, we actually contributed to the Java key store support for MR connector and the TiKV client, which MR connector uses internally. MR connector scalability issues, these were resolved mostly by PingCAP folks. This was needed because the table which we were snapshotting here, it was pretty big, of 4 terabyte, and probably the tool was not used at this scale before us. So yeah, they helped us solve the scalability challenge. So a little bit of background about the 4 terabyte use case which we have migrated to TiDB. So it's called admin history store. It basically tells what actions we have taken against a Pinterest user and their content and why. We check if that action is already taken, so that we don't take the same action for the same infraction. We have a lookup.pinadmin.com, which provides a view of state of the user, board, domain, image signature, etc. We generate a biannual transparency report stating all the actions taken against users and content. So that's why we need strong consistency for it, because if we are standing up to the world saying that this data store represents the sum total of admin actions, they should be right. These are the big wins after the migration. We saw 3 to 5x P99 query latency reduction even after having 14 indexes. So it's a distributed SQL, right? So indexes are supposed to basically increase the write. Indexes help in reducing the read latency, but they do increase the write latency because you also have to write to the index table. So that's why we have to make a trade-off when creating an index. So we saw 3 to 5x P99 query latency reduction. This use case has 20K read QPS and 400 write QPS. So we didn't see much increase in the write QPS even after having 14 indexes. Now we have strong consistency guarantees. So this report, which is published, is accurate. We have simplicity in architecture. So Exia a system consists of 6 components, and now it's just the API service and TiDB. We have made more than 4 contributions to open source community as a part of just this exercise. We were able to achieve 5 nines of data consistency between HBase and TiDB. We were able to migrate 4 terabyte of data in 9 hours and reconcile any inconsistencies which were created in 8 hours. So we are able to like bring up a new TiDB clusters in 2 to 3 business days for a 4 terabyte table. Admin history store is running on TiDB for more than 3 weeks with no manual operations needed for cluster management. This is a big win because in case of HBase, we have a lot of manual operations. For example, splitting huge regions, compaction, and there are a lot more which I don't remember at this point. But all of these are actually automated by our engineers as Puppet, but sometimes they do fail and they do come up as surprises. For TiDB, we have not done any automation around for this. So that's why there are no manual operations. Future work. So basically our goal here is to ultimately deprecate HBase. Going forward, we will continue reliability improvements on TiDB platform at Pinterest, continue migrating existing Exia use cases which are powered by HBase news to SDS TiDB. SDS is the data access layer. And then we want to put TiDB offline framework in production. We are using TiSpark for it. We also want to put some effort in TiDB CDC framework and integrate it with Pinterest CDC. And then we want to start migrations of Zen, Sparrow, and other legacy services at Pinterest like contact service. These are the acknowledgements. I just touched on two major work streams, which is TiDB infra and data migration. But as you can imagine, bringing a new storage system in at scale of Pinterest is a huge challenge. And these are all the team members who are working on different work streams, and they will be presenting in future meetups. So I would like to thank our management, Bo, Dave, David, and Liang Hong. Liang Hong is my manager of storage and caching team. Engineers, Alberto, Anish, Bin, James, Kerr, Kevin, Lichi, Mark, Purajit, and Vivian. This project has been going on since 2020. So we had 3 summers where interns came and contributed in different work streams. I would like to thank Antonio, Andreas, and Sangeeta. From PingCAP, I would like to thank Adamo, Colby, Leo, Sean, and all the SMEs. So these are our main points of contacts, and they pull in all the subject matter experts whenever needed. And internal Pinterest teams like Telatran, which is the deployment service, security, Hadoop, Spark, Artifactory, and SRE, and all of our customer teams for showing faith when we do this migration. Thank you.
Yeah, okay, so you can join our groups. This is WeChat group, and we also have Slack group, and you can also sign up for TiDB Cloud. And we do have lots of PingCAP course, PingCAP learning course available. We have TiDB technical essentials and TiDB architectural basics. You can scan this barcode to join this course. And the Japanese version will be ready very soon. You can also. Yeah.
Thank you so much.
Yeah, we do. Yeah, we do have courses in other languages. Yeah, that's everything from my side.
Okay, thank you, Zhenghao.